So, how do we know that these perturbations are reliable? Well, you compare it to observations. That's about the only thing that we can do, essentially, to decide whether we have done a good job of characterizing the input uncertainty. So we want the true evolution of the system, shown in green here, to be within the envelope of the ensemble. We don't want it to be outside the envelope. Because if it's outside, then we either miss the variability during that period, or our model is bad. It's hard to say. So this is sort of a qualitative aspect. So since our interest is in the location of the loop current, we looked at VISO data. So these are altimeter observations that are shown in color and in the white line. And so that's the estimate of the loop current edge during that from observations. And we have overlaid on it the estimate from the 49-member ensembles and from the 800-member ensembles. Okay. And so by and large, you can see that the model, the ensemble is tracking the location of the loop current actually quite well for the extended period. Okay. And so, at least as far as the sea surface height is concerned, it looked like we're doing a relatively good job. The problem that will become apparent later is here, where it looks like the model is trying to put another frontal eddy here, but the observations are not seeing it. Okay. But in other places, we're doing a fairly good job. Okay. We compared also against current observations. The Bureau of Ocean Energy Management had a bunch of moorings that we could use to compare essentially the currents, the variability in the currents against the variability that we were seeing in the ocean, and just by the eyeball norm, essentially the ensemble is really capturing what actually has been observed, especially at the surface, right? It looks like this one mooring kind of, the ensemble is underestimating, the 49-member ensemble seems to be underestimating the variability that was measured by the mooring, but when we add in the other members, they seem to inflate the variance in the ensemble. We're in the right ballpark, at least there. Look, we did a decent job of capturing the uncertainties of the day. So the other thing that we asked ourselves, so we went from a 2-dimensional space to an 8-dimensional space. How much did we gain? Did we do the right thing by adding the higher order mode? And how much information did we lose if we had reduced our system and made it smaller? Okay. And so we quantified this loss of variability using the relative entropy, which you've heard a lot today. And essentially, the only way you can obtain these quantities is by having a surrogate. So you could actually estimate the PDF of the output. Okay. And so we performed experiments. Our reference calculation is when we perturbed everything. Our first thought is, do you really need the higher order modes? Because essentially, the principal component, the eigenvalues are decreasing in magnitude. How much do you lose? And what happens if we just perturb the initial conditions, like in our first experiment? How much do we lose by perturbing just the wind? And so we're going to measure that using this relative entropy measure. And so the top figure shows what happens when you throw away the higher order modes. It's essentially blue. That means you really didn't gain any variability. There's no information loss. There was no point in increasing from 2 to 8. Increasing from 2 to 4 would have been enough. Omitting the winds would have essentially cost you variability in the shelves area. Okay. And putting only the wind and not the initial conditions, you would have missed a big portion of the variability in the loop current system. Okay. So the moral of this is you're much better off putting only a portion of the variability that are kicked in by the EOS and adding other sources of variability. So if I were to do this again, I would put maybe heat fluxes as uncertain on the surface. Just 2 mode, 6-dimensional space. This is essentially a comparison between the sea surface height, the PDF of the sea surface height in the different areas, and not a lot of them look Gaussian. So we're comparing them against the Aviso, which is in red, and the HiCom from the ensemble are in blue. In a lot of places, the Aviso turns out to be narrower than the ensemble, and we're not quite sure how to interpret that. Okay. In the loop current system, you have essentially lost predictability fairly quickly here, for example, because the 2 PDFs look quite similar. Let me skip this. And again, this is looking at a particular point in this loop current system, producing the SSH PDF of the output. This is the magenta line. It is highly non-Gaussian, essentially bimodal. And so if you're doing data assimilation, assuming Gaussian PDFs, you're missing it quite a bit. And so what we did, so if you're replacing the red lines, right, the actual output with this blue line, if you're just looking at the mean and the standard deviation as your parameters. And so we did this over the entire Gulf of Mexico, and the regions which are red are places where the Gaussian assumptions is totally broken. Like the distance between the 2 PDFs as measured by the relative entropy is greater than 0.4. And of course, it is in the places where the loop current is detaching when you have strong bimodality. Okay. So if you have data, the next thing that you want to do is do some sort of inference. And this is the work that was done. So we took the tracks of the altimeter data as our observations, and we tried to guess what the right modes for the uncertain inputs would have to be. Okay, and we did it only with the 49-member ensemble because the uncertainty in the sea surface height was caused by the 2 initial condition modes. There was no point using the 800-member ensemble for this exercise. And so this is what you can clearly see, the detachment of the loop currents. It's right on the observations, but the northern extension is actually a little bit different than what the models were producing. So let me show you. So this is our Bayesian inference, and so the 2 parameters that we're getting are the amplitude of these modes, including the uncertainty in the error in the observations. So all of this is our hyperparameter here. And so we're using the surrogate. These are the observations. These are the model output from the surrogates. And we're doing an MCMC over this parameter space to infer them. And so this is the chain of the MCMC. And as you can see, it converges towards these values fairly quickly, actually. So it's a well-mixed change, and the parameters in the parameter space turn out to be fairly well located. This is the maximum a posteriori. The data is saying that your Xi1 has to be slightly negative and very close to 0, and your Xi2, the amplitude of the second mode, should be closer to -1. And if you were to do an RMS measure between, so this is our samples. There's no interpolation here. And so if you're measuring the RMS error between these 2 quantities, the minimum you get is actually here. And so we look back at what, so you can actually look at the actual simulation and to see what the data is telling you your initial perturbation should have been. And so this is the location. So I'm going to show you the two extreme of this. And this is located here. So the horizontal axis is the most negative perturbation along psi 1, the unperturbed one, and the strongly perturbed one. They 10, 20, and 30. And so, and this is the data. So, and if you notice that in the necking region, right, the model and the observations are fairly close to each other, right? Where it departs at day 30 is when the models are trying to put another frontal eddy here, whereas the observation are not seeing something like that. So the model is pushing towards removing that eddies and putting this eddy in. The Bayesian inference is trying to enforce that. All right. All right. So we did it in two different ways, and the other technique we used is Bayesian optimization, and it pretty much gave the same results, whether you're using the Monte Carlo sampling or the Bayesian optimization. So our data ensemble comparison show the uncertainty generated by the EOF modes does a fairly good job at representing the observed variability in the loop current regions. You don't need to include all the variability that you see in your EOF decompositions. It's enough to knock the system with the leading EOF modes to keep the parameter space small. At least this is true for this 30-day forecast. Maybe if you went longer, things would change. Putting the wind variability was very important if you're forecasting the shelf circulation. Without it, you would be missing the variability. If you didn't care about the shelf circulation, you're okay with throwing away the wind perturbations. Okay. It is more important in general. This is what I learned from this, is to put different type of uncertainty sources than adding more modes. If you want to grow the dimension of your input space, this seems to be the message here. Okay. It looks like the loop current separation predictability, given the perturbations that we've given it, is about 3 to 4 weeks. And the SSH PDF shows strong non-Gaussian signals. So, in my view, polynomial chaos is a very promising thing for ocean modeling. There are still some challenges, especially with sampling for high-dimensional problems. And most importantly is essentially the head-scratching that you need to do to identify the uncertainty in your inputs. How to characterize the uncertainties with the minimum number of uncertain variables. And so we've been relying on EOFs for all these things. They're very powerful. We haven't tried anything else, mostly because we don't have an adjoint for the models. We cannot find the singular values or the breadth vectors, which require an ensemble to actually identify them. Making ensemble of ensemble seems a little bit too much. And so, and utilizing PC tools and data assimilation is still a work in progress for us. That's it.
You don't use SST information instead of wind. So you said that wind is important for the shells, and what about the SST information?
Well, the heat flux, it's uniformly hot in the Gulf of Mexico during May, And on this 30-day period, we didn't think that the heat flux would really impact the circulation that much. Not compared to wind or initial conditions. But if I were to do it again, I would add 2 modes of heat flux at the surface, or maybe 1 mode.
And concerning your EOF modes, so you compute them separately for the wind and separately from the SSH.
Yeah.
And what about combining the two information and you know this kind of bivariate EOF analysis? Try to find the the PCA, the EOF
for the combined wind,
for the
initial
combined
conditions.
wind and SSH. Did you try that?
Well, for an ocean-only models, the wind forcing is just imposed. I mean, in the physics of the problem, they're coupled. Mm-hmm. But in the way we're running the models, they're coming from a separate source.
Ah, okay. Mm-hmm.
So we didn't combine them as such. Moreover, for the initial conditions, you need previous information. Mm-hmm. What was the variability 2 weeks before I saw the computations? For the wind, you need information during the calculations. What is the variability in that 30-day window? Mm-hmm. And if you think about it, 30-day window in an atmospheric forecast model is actually fairly long. You wouldn't trust it beyond a day. Mm-hmm. What we're using here is a reanalysis product. So we're kind of cheating a little bit.
Okay. And a last point is about the comparison with the observation, the true mooring in situ data. It was not clear for me. Just can you come back to this slide? It was difficult for me to read the results.
Okay. I put a bunch of articles that describe PC and ocean models and things like that.
Okay.
And let me go back to the.
Yes.
Oh, here.
This one.
Yes.
Can you?
So this is a busy slide. I should have just put 2. The blue slide, the blue arrow. You can see one here on the edge. Yeah. Is the mean of the mooring over that period of 1 month. Okay. And the black lines are the mean of each one of the ensemble members. Okay? Mm-hmm. And so here there are 49 black arrows and 1 blue arrow for the data. Okay. The ellipses are trying to represent the variability in the velocity, and the vector velocity over that period. Okay. And so there's a blue line, which is embedded here in the red.
Okay. I didn't see the
and
blue
it's
line.
very hard to see it.
Okay.
I apologize for these things.
Okay, okay. Now it's clear enough. Okay.
On your question, this is in fact quite important. And it's unfortunate that in an ocean model, in this particular case, we have to analyze the winds separately from the initial conditions because they're coming from different products. But some of the failures that Mo alluded to are due to this fact. I mean, if you have a lot of wind and no waves, or the state is very mismatched from the state of the wind is very mismatched from the state of the ocean. The ocean is going to respond in a very dramatic fashion. We're going to have overturning circulations, things like this, where we really need not sample those silicon. It's really unreasonable to have 50 meters per second wind and no wave at all. But in this way of building the initial conditions, it is very much possible that this is part of your prior, even though, you know, common sense says we've never seen these conditions, nor should it be acceptable to see. Mm-hmm. In a ocean only, we don't know how to do that, and this is one of the reasons why we started looking at ocean, atmosphere, wave models all coupled together. Okay, are much happier, but these extremes that are unreasonable that we should rule out from the beginning, we don't know how to do them in that other sense. Mm-hmm. And they lead to push the code, outside the comfort zone of hierarchizations, or they cause events that are never seen just because of the system has to rapidly adjust to conditions that are way out of balance.
Any other questions or comments? No? Okay.